Hello everyone, welcome to my next session on system Verilog assertions. So in this video we will discuss what assertions are, why they are used in verification environments, and how to write and apply them effectively in system Verilog. So we will start this session with a quick overview of what assertions are, followed by why the assertions are important in system Verilog verification. Then we will discuss what is immediate and what is concurrent assertions, followed by examples and few common operators used in assertion. Towards the end, we will wrap up with a quick summary and we will apply all the understanding to a small problem to see what we have learned. So what are system Verilog assertions? Assertions are statements used to check if something is true in your design. So they are like automated conditions that monitor whether your design is behaving correctly or not during the simulation. You can think of them as automatic checks that keep verifying the conditions for you without writing some extra test logic. So if an assertion fails, it indicates that something unexpected or something incorrect happened in your design, and it means there is some bug in your design or in the test bench. So what would happen if an assertion fails? In that case, system Verilog simulation will print an error message either to the console or to the log file, and it will also mention which assertion got failed and at what time. You have the option to configure it, means you can configure that if assertion fails, then simulator can be set to stop immediately or it may continue further. So there are few examples to understand how assertions can be written. So first one is a simple example. Here we have mentioned that if reset is asserted, then output must be 0. So this check will ensure that your design reacts properly to a reset condition. In the second example, we are checking that write and read should not happen at the same time. So this is a kind of protocol check, and we use in case of FIFOs or in memory controllers, etc. So you can see with just a single line, we can add meaningful design checks that can catch bugs early in the verification cycle. So now let's talk about why we should use assertions in our design. So assertions are useful because they help you detect logic bugs immediately in the design. So as soon as a condition is violated, you will know it immediately during the simulation. And it also means you can catch bugs early rather than finding them late when debugging becomes very time consuming. Next is they are good for protocol violations, like we have already seen the example of simultaneous read and write conflicts. Assertions are also helps in documenting the design behavior. They tell others what the design expects and how it should behave. Also, when you insert uh, assertions in the design, your simulation becomes more smarter. They also helps in debugging. When a test fails, assertion can quickly point to the root cause. Over the time, it also helps in improving the confidence in the design. If your design passes all the assertion checks, it means you are more certain that the design is behaving correctly. Finally, assertions are also essential if you want to move into formal verification. So overall, assertion saves time, increases reliability, and help you write better, more robust designs. So assertions in system Verilog can be categorized into two types, immediate and concurrent. So immediate assertions are those checks that occur at a single point in time. So for example, you can think of them like an if statement that throws an error if a condition is false. For example, consider this assert statement. It checks immediately whether the ground signal is not all jets. So immediate assertion means instant check. They will check immediately whether the assertion is true or false. Next we have concurrent assertions. So in the concurrent assertion, we include those checks that happen over the time. Means they are spread across multiple clock cycles. So there is an example to understand these concurrent assertions. Here assert, we are using a property. So this checks that if rec is high on positive edge of the clock cycle, then grant should follow exactly one clock cycle later. So let's understand this statement. So here this at the rate passage of clock, this is the clocking event. It means the assertion should trigger and evaluate on every positive edge of the clock cycle. Next we have a condition, rec. It is like a if condition, and if it is true at positive edge of the clock cycle, only then rest of the assertion is evaluated. If it is not true, then rest of the assertion is not evaluated. Next we have this implication operator. So what does it means? This implication operator means whatever we have written on the left side of the operator, if that is true, only then right side must also be true after the specified delay. And how do we specify the delay here? So this is the operator cycle delay operator, and it means after exactly one clock cycle. So grant should be true one clock cycle after rec becomes true. So if I again read this statement, it means on every positive edge of the clock, if rec is true, then grant must also be true exactly one clock cycle later. And if it doesn't happen, it means the assertion will fail, and it means there is a bug in your design. So let's understand each assertion type separately. So in system Verilog, immediate assertions are evaluated instantly. So right when the simulator executes the statement. They are used inside procedural blocks such as always initial, always FF, and they are also used for combinational checks. The syntax for assertions, immediate assertions, is very simple. Assert and the condition. For example, assert A equals to B. So this ensures that the value of A equals B at the time of execution. In the next example, we have assertion if start and done both are high at the same time. So this ensures that start and done signals are not high at the same time. This is a common check for preventing overlap in the control signals. So if the condition fails, simulator will throw an error and may halt the simulation until and unless you have specified some other action in case of assertion. Like you always have the option of configuration, like you can configure it in whatever way you want in case of assertion fails. So next we have concurrent assertions. Unlike immediate assertions that check conditions instantly, concurrent assertions check across the time, means across multiple clock cycles. They are used for temporal checks to ensure that certain events happen in a specific order over the time. So concurrent assertions are perfect for verifying sequence of events. So for sequence of events, we first define sequences and then properties and then assert those properties. So for example, consider this example. Here we are defining a property P example. Inside this property, we are defining a clocking event. So this checks that at every positive edge of the clock cycle, if signal A is high, then on the same cycle, signal B should also be high. This is another example. Here, here we have defined a property called handshake. Inside this property, we are mentioning that at every positive edge of the clock cycle, if request is high, then acknowledgement should be high exactly one cycle later. So these assertions are very useful for checking handshake timings, event ordering, response latencies. So in short summary, concurrent assertions help us track and validate time-based behaviors that is critical for design correctness. Now let's understand sequences in System Verilog. So sequence is simply an ordered set of events. Those events which happen cycle by cycle. So to write sequences, we use few spatial operators. For example, this hash hash n. It means a delay of n clock cycles. So this is how we specify timing delay between the events. Next is the implication operator. It means if event on the left happens, the event which is mentioned on the left hand side of this operator, if that happens, then the event that is mentioned on the right side, that must also follow. Next we have this star n operator. It is a repetition operator and it tells the simulator to repeat a condition n times. For example, like in this case, we have defined a sequence S, and this means if A happens, then after one clock cycle, B must also happen. In the another example, if start is high, then after exactly one clock cycle, busy should be high, and after exactly two clock cycles, done should also be high. So sequences are very useful for modeling protocol timings or transaction flows or even state transitions. So let's go through a simple assertion flow. For this, we first describe a sequence. And in sequence, we define an ordered set of events. So here we are defining a sequence S. Inside this sequence, we are defining a set of events. For example, here we are defining an event that if A occurs, then B must also occur after two clock cycles. Next, we wrap the sequence in a property. So for example, here we are defining a property P. Inside this property, we are using a clocking event that every positive edge of the clock cycle, if sequence S occurs, then C must also occur in the same clock cycle. Finally, we use the assert keyword to assert the property. So trigger this will trigger a failure if this condition doesn't hold, the condition which is mentioned inside this property P. So this diagram also explains it. First we start by checking if A occurs. If A happens, then we wait for two clock cycles, and after two clock cycles we expect B to occur, and finally we check for C. So this is a three-step flow. First sequence, then property, and then assertion. So this is another example of using assertions in System Verilog. Consider we are working with a design where a read enable signal must be followed by a read data valid signal. So this is how we can write an assertions to check this. So here we are using a property and then we are asserting that property. So inside that property we have added a condition that on every positive edge of the clock, if read enable is high, then exactly after one clock cycle, data valid must also be high. So assertions like this are not just theory, but they are directly applicable in verification environment at industry level. So this is another example of using system Verilog assertions. So in this example, if read enable goes high, then data valid must also be high within 2 to 3 clock cycles. So to check this, we have defined a property named read underscore timing. Inside this property, we are checking if read enable is high, then data valid must also be high after a delay of 2 or 3 cycles. This property is then asserted using this statement. So the assertion will be violated if data valid becomes late and it misses this window. So this kind of assertions are very helpful in verifying timing relationships in protocols. So let's now explore a slightly more complex example. So in this scenario, the start signal must be followed by done within 4 clock cycles, and during that time reset must not be activated. So to add this check, we have defined a property named p start done. Inside this, we are defining that if start goes high, then reset should be low, and done should be high within 1 to 4 clock cycles. And then we are asserting this property using this statement. So the flow can be visualized like first we have start, then there is no reset for 1 to 4 clock cycles, and then we have done. So these kind of checks are very important to verify that operations complete on time and without unexpected resets during the execution. So we have one more example which checks a condition where write enable is only allowed to remain high for up to 4 consecutive clock cycles. So to check this, we have defined a sequence burst underscore write. Here we have written a statement like this. So if you remember, this is a repetition operator. So it would match when write enable signal stays high for 5 or more consecutive clock cycles. Then we are asserting that such a condition, such a sequence must not occur. And why such a sequence must not occur? Because it says that write enable signal should be high for 5 or more cycles. But what we need to check? We need to check that write enable can only be high up to 4, not more than 4. That's why we are asserting that such a sequence must not occur. So these are industry standard simulators that support assertions like Synopsys VCS, Cadence Xcelium, and Mentor Questa. So these tools allow you to use assertions not just in simulation but also in formal verification. So let's wrap it up with a quick summary. Assertions are very important for validating your RTL designs. They help you in verifying correctness and catching bugs early in the verification cycle. Immediate assertions, they check conditions at a single point in time. Concurrent assertions, so basically these are those checks that are spread across multiple clock cycles. Assertions are easy to write and they are extremely powerful. And finally, you can practice using real protocol examples, and that is the way to build confidence and mastery in assertions. To understand and to see what you have learned, you can try solving these two problems based on assertions. And once you are done writing the assertions, try verifying them using a test bench. If you would like a hint or you want to cross check, you can do so by checking the next slide. I have added the solutions in the next slide. If you would like to learn more or need help with any training or consulting, please feel free to reach out. You can contact us by sending an email to scguru.tech@gmail.com or by connecting us on LinkedIn. Thank you.